Good evening. This is the third in the webinar series from Oregon Hanford webinar series, and this is the one about groundwater protection. First, I'll introduce myself. My name is Dale Engstrom, and I'm the hydrologist on the staff. We're not going somewhere here. Oh, man. I'm just trying to get it to go to the next. Okay, thanks. So my name is Dale Engstrom, and I'm the hydrogeologist on the Oregon Department of Energy staff. And what does that mean? That means I'm interested in how the water moves the ground and how stuff in the ground affects the water chemistry and how the water actually moves through the ground. So why is that important? Why is Hanford groundwater important to Oregon? So the first thing I'd like to do, I'm going to put you on the spot right away, is I'm going to ask a poll question, Becky. And the poll question is, why is Hanford groundwater important? So the first answer is because the radioactive elements might cause a nuclear explosion. Number two is because Oregon wants to help regulate what happens in Washington State. And number three is because the groundwater contamination will make it to the Columbia River, and the river is important to Oregon. So pick one of those, please. I didn't fool you a bit, did I? Everybody went for the contamination, and that's the answer. And I think actually the first presentation we had, Ken Niles talked about how important the Columbia River is, and that's really why Oregon is involved with this whole thing. That's really why we're here, and we're working with the tri-party agencies to do something about Hanford. So here we go again. So what am I doing wrong? Oh, thank you. Okay. So let's start again. We've done this before, but let's start again about where is Hanford and how does it relate to Oregon. Hanford, up in that little map up in the top left, you can see the Hanford site sits in Washington just north of the Oregon border, and it sits cradled in a curve of the Columbia River. The Columbia River was important because, as we'll go on a little bit later, that's where they wanted to put the reactors. You can see the Hanford site was a really large piece of ground, and the man that found it, the Army colonel that went out looking for the right place to put these reactors back in the early 1940s, found this place because of the Columbia River. He thought that was a really neat thing. So if we look at Hanford geography, really in terms of how it's being used by people, you can, from this, what looks like an air photo, you can actually see Hanford because it's where the farming does not happen. You can see the green areas all the way around the upper left, off to the right, and to the south you can see green all the way around Hanford, and you can actually almost see the border of where it is. And then it goes down to the lower left to the ridge of that mountain, and that's the Hanford site. And so the important part of this thing is it's a really big site that hasn't had a lot of human use on it in terms of farming and that kind of stuff because it's been closed off for the nuclear things. Okay, so what, in terms of groundwater, we want to look at the Hanford site for areas that are important to the situation. So let's talk about some of the key areas at Hanford and the things that are happening there. So these red circled areas are the sites where they put the reactors, where they sent the uranium fuel rods, and they put them in reactors, and they made them by irradiating them, by self-irradiating. They created plutonium, and the plutonium is what they wanted to make the atomic bombs out of later. So the reactor areas are along the river. They did that because they needed the water from the river to cool them off. And this, of course, you've heard before, is the central plateau, and they would take the fuel rods from the reactors and they would run it down to the plateau to the 200 West area and the 200 East area, and those areas were where the big plutonium processing plants were. And this is the place where the rods were dissolved, the plutonium was extracted, and then they had to get rid of that material somewhere, and we'll talk about that in a minute. So out in the 200 west and 200 east area of the Central Plateau, there are lots of tank farms like Dirk was showing you last week. There's lots of solid waste burial grounds you saw pictures of when Ken Niles was talking. There's liquid disposal areas where they used to put liquid waste right in the ground and let it soak in. And so all of these places were in that 200 west, 200 east area. And the reason there's two of them, there's an east and a west, is because they wanted duplication in case something happened in World War II or even during the Cold War. If somebody blew up one of them, they'd still have the other one to still be able to make plutonium. That long rectangle at the bottom, that ERDF, ERDF stands for Environmental Restoration Disposal Facility, and what that is a giant landfill where they're taking all this stuff when they're remediating. They're cleaning up the Hanford site. They're taking all the stuff up there to ERDF and they're putting it in a giant landfill. Okay, that's the Central Plateau. And the other area we're going to talk about is the 300 area. And basically that was the laboratory they set up to be able to develop the processes that they used in all of this whole process. And so they used to build the uranium fuel rods there. They came up with the different kinds of processes to dissolve those rods. They had, over the decades, several different processes that they came up with. And they also did a lot of other experiments. Okay. So moving right into the groundwater then, this is the part that I'm interested in. This is a groundwater plume map. So these colors represent elements that are considered contaminants that have gotten into the groundwater and they've moved over the decades. Now first of all, that large sort of yellow tan area on the outside is just a land area. That basically is what they call the Hanford Reach, and it's fairly clean, and it's been actually released from Hanford and is now being controlled by the U.S. Fish and Wildlife. Excuse me. The tan area is actually Hanford, the Hanford that they are worried about. And the dark brown areas are all areas that are areas where they're doing operations. So if you look along the river, you'll see there are 6 different reactor areas in brown, and each one of those areas has contaminant plumes with it. The light blue there is chromium, that's chrome plumes, and the yellow is tritium. And every once in a while you can see a little hint of purple. That purple in there is strontium. Strontium is one of those things we have to worry about because it's a radioactive element that's dangerous to the environment. Okay, so moving on a little bit, that central part there, the Central Plateau, excuse me, there's the 200, oh sorry, there's the 200 west area and the 200 east area. If we go to 200 west first, the facilities at 200 west, again, were dissolving those rods. They were disposing of stuff into the ground, and so naturally the groundwater there is very contaminated. And so there's a number of different plumes there that are very complicated. The uranium is kind of important. That's the red is kind of important because that's uranium. The pinkish area to the 200 west side is actually carbon-tetrachloride, and that was one of the solvents they used to use in that process when they dissolved the rods on that side. You can see there's still light blue areas that are related to chrome, and there are some other spots in there that are, the green colors are really iodine-129, which is another radioactive element that's fairly ugly. If we go to the 200 east side, you can see that compared to 200 west where the plumes did not move very much, 200 east the plumes went a long ways. They went all the way down to the southeast to the river. They have been to the river and in the river, and they're going up to the northwest to the river, to the top. And so what you're seeing there is light yellow is tritium. Tritium basically is hydrogen, and it hooks up with water, and it travels as fast as the water does, and it's already been in the river. The iodine plume, which is fairly dangerous, is about halfway to the river. That iodine plume is something like 10 miles long, and it's something that we're very concerned about. And also there you can see the purple. The purple colors are strontium. The reddish little blob there is uranium. The light blue color is technetium, and technetium is one we haven't talked about. That's another radioactive element that comes from the process of making plutonium. So you can see that this is a very complicated picture, and there's a lot of concern about what's going on in the groundwater. A lot more is going on in the groundwater than you would first think. So let's move on and look at some of this stuff. The oldest, we're going to go to the river first. along the river, they built the reactors. This is the oldest reactor. It was the old B-Reactor, and they basically just named everything by the alphabet. So they had an A reactor design, but they never built it. So they started with B, and B and C are in the same place, and they look almost identical. And so that's the B-Reactor. And if you go inside the B-Reactor, the face of the B-Reactor looks just like this. And by the way, you can take a tour that's open to the public that'll take you there, and you can sit with those folks and look at that reactor face. It's really fascinating. What they did back in 1943 and 4 was absolutely amazing. They built this building in 18 months, doing a process that nobody had ever done in the world before, and it worked. It worked very well. Okay, so why were the reactors put there? The reactors were put there because they took raw uranium fuel and they exposed it to radiation, and they created little bits of plutonium in there. The reactors had to be placed close to the Columbia River because they used the river water to cool off the reaction. And it was never meant for making electricity or anything else. It was just simply to make plutonium inside those rods. At the same time, other radioactive elements, we were talking about carbon and cesium and strontium and tritium and uranium, so forth. They were also produced, and those elements, because of the way they did things at the reactors, escaped and they got into the ground. At the same time, they brought in hexavalent chromium, bunches of it, tons of it, and they added to the cooling water to control the corrosion, and then chromium is very toxic to most organisms, especially the ones in the river. So if we look at a typical reactor area, this is the K100K reactor area. A picture was taken in 1965. You can see there are two reactors, and the reactors are those buildings that have the smokestacks on them. So starting from the beginning, the water was brought in to those ponds, those rectangular ponds you see on the right-hand side. And those ponds were the siltation basins that basically the silt and the sand was allowed to fall out of the water so that you wouldn't get it into the reactors. And those dark brown lines you see to the right, those are rail lines, and they would bring in the hexavalent chromium right there, and they would dump it into the water and treat it, and then they would send it to the next building to the left, which is the big pump house. The pump house pumped it into the reactor. The reactor, it's a one-pass system, so they would put it through the reactor as fast as they could, because the reactor is so hot they had to make it really quick. And then that water went out to those three tanks to the left, and you can see how hot it is because they're steaming like crazy. Both reactors are running in this picture. You can see all the steam. From there, the water was allowed to cool off, and then it was sent to that long zigzag trench at the top of the picture. And there it was allowed to soak into the ground, was the idea. But they put so much water in that trench, and they did it so quickly, and so much water was being used, that a lot of it escaped very quickly. And you can see at this end of the trench, the one that's closest to you, there's a lot of water that's getting out, and there's areas of standing water and a lot of greenery where the vegetation is growing, where the water is actually getting out of the trench and making a shortcut to the river. Okay, so this is a typical reactor area. There were 3 reactor areas that had 2 reactors in them, and there were 3 reactor areas that only had 1. And so there were basically 9 reactors in the 6 areas. Okay, so let's look at this area now that is being cleaned up. So this is the same area. The reactor next to you is the same reactor that was the closest to you before. And you can see there's a vast difference between the far reactor and the close one. The one in the far distance is the east reactor. The one that's closer to you is the west. And you can see at the east reactor, they've removed a lot of the buildings around the reactor, and they've dug some holes around there, digging up some of these sites that have contamination in them. You can see at the west reactor, the one that's closer to you, that the siltation ponds are gone, and all that load-out stuff where the train tracks used to be is gone. And there's also some big holes dug there where they're going after the hexavalent chromium. Okay? So let's zero in a little bit on that far reactor, the east reactor. So over here to the right, was one of those hexavalent chromium areas, and you can see they're digging a big hole, going down, following the chromium into the sands and gravels to see how deep that goes and to remove that soil and take it up to Erdf. The building to your upper right, up here, this building is the pump house I was talking about, and so the water used to come out of here and it would go through pipelines like this one. It would go to the, it would go to that, Anyway, it would go to that reactor, and it would flow through the reactor, and then it would go to the river. And you can see the arrow to the left shows the river, the direction of the river, and this flat face right here in the front of the reactor is right behind there is where the reactor was, the reactor itself. And they used to take the spent rods out of the reactor and push them out this side of the reactor, and they would fall into the spent fuel basin, which is right there in front of the reactor. The basin itself was not actually formed as part of the foundation of the building. It was separate, and there was a crack. There was a seam there, and there was a lot of water that got out of that seam and went down below the reactor. So there's this large plume that sits right in front of that reactor, and it's a problem because they're not going to remove the reactor. They're going to leave them there. I'll talk about that in a little bit later. And then there's another area up here where they're digging a carbon-14 plume. And you can see that they've removed all the buildings all the way around this thing, and they're now removing dirt down to the point where they feel it's clean enough that they can leave it. Okay? So that's how they clean up a reactor waste site. And the reactors then will be what they call cocooned, which means they'll have a roof put over them to keep the water out, and all the sides are sealed up, and that block will sit there. They plan to leave those things for like 75 years until the reactor core, the fuel's been removed, but the reactor core itself has to cool down, and it's going to take approximately 75 years to get there. So then the irradiated fuel was sent up to the central plateau to those plutonium processing plants I was talking about. They were dissolved, and they took out the uranium and the plutonium. And the problem was there were a number of different plutonium dissolving chemistries that were used over the many decades of processing. It went from 1940 something up to like 1980 something, so there were like 4 decades of doing this stuff. The worst of those waste liquids were sent into the tanks, the tank farms that you saw with Dirk last week. The rest of the liquids were disposed into the soil in ditches and ponds and cribs and things like that. And some of that liquid that wasn't so bad actually went to the ponds. I should have made that separately, but they were a little bit less bad liquids. And then the solid waste that they got out of this processing process, they would, and some liquids actually, all went up to the burial grounds and they buried them. And those are the pictures you saw with Ken Niles where they had the big barrels that were throwing in the ditches and putting dirt over the top. So what do one of these plants look like? You've seen this picture before, I think. This is the T plant under construction. This was the first one they built. This is back in 1944. That thing is something like 1,200 feet long, 7 stories high. It's like 2 or 3 stories into the ground, basements, and it's something like 100 feet wide. Just for scale, if you look to the left, you can see train cars, full-size train cars, and they're dwarfed by the size of this building. It's a huge facility. Here's 2 of them right now. There's the T plant that I just showed you and the U plant. They just, again, go by letters, the alphabet. Here's the inside of the U plant. This is the interior. There was a crane that ran back and forth on that upper ledge, and that inside interior there is made so you can lift those panels off of the floor, and there's these big hot cells down below there where they could work on radioactive material and not expose people up above. So it was a very big facility. They did lots and lots of chemistry in these things, really dangerous kind of chemistry, and there were lots of leaks. There were things that got away. Okay, so this is the typical sort of setting around one of these plants. U plant is actually off to the left right there in the upper left-hand part of your picture. There's also Redox, which is another kind of a plant that came along later in a different kind of a process. And so the fluids would come out of U plant. They would be sent to the tank farms. Just happens that sitting in front of you is the SX and SY tank farm. Actually, they're very, there's not much to see at a tank farm other than little pipes sticking out of the ground, because everything's been buried, and some of these tanks are huge. They're like 1 million-gallon tanks, and they're sitting under the ground, and they have this dangerous waste stored in them. So that's the really hot waste went in there. The medium waste went out to trenches, and I don't have a good picture of that right here. And then the least bad fluids would go out to the U pond or other ponds, and they would soak in out there. But for the most part, all of the liquid waste that they were trying to get rid of, those liquids were allowed to soak into the ground. And the theory was they were going to attach to the soil, and they would just hang there forever. Well, of course, that's not true. This is what tanks look like under the ground. If you can see, if you saw through the ground down to what they look like, and they typically came in 12s, 3 by 4, And like I said, many of them were 1 million gallons in size. So if we look at a tank farm, I know Dirk was showing you tank farm construction and that. If we look at tank farms in terms of what's in the soil, this is the BX, BY, and B farm, and you'll see BY again. You can see that within the BX tank farm, over to the right-hand side, where it says BX 102, there's actually some pretty big numbers. And if you look at the radionuclide symbols off to the right-hand side, the second smallest bubble is a cleanup level. So if it's that second bubble or bigger, it's dangerous waste. Okay, and so anything that's larger than that smallest bubble is something we have to be concerned about. And you can see that the BX tank farm has some really big bubbles for uranium, for strontium, and for cesium. And those are obviously coming out of some tank right there, probably the 102. Even more concerning for me is that trench, the ditches up above to the north above the BY farm, and then they have huge amounts of Tech-99, the technetium. There's some uranium, there's strontium, and a little bit of cesium. And the ditches to the left, which should be west, also have quite a bit of cesium, and they have a little bit of strontium as well, and uranium. So you can see that where they dispose this stuff into the soil, we can go now and pick up soil samples, and we get some really big numbers out of the thing. This material is arguably mobile, and as precipitation gets on it and so forth, it moves through the ground, it goes down through the vadose zone, and it becomes part of the groundwater. This is what's going towards the Columbia River that we have to be concerned about. So just to give you sort of a visual on what's going on with tank leaks, this is the SX, we saw the SX tank farm before, this is the SX tank farm, and you can see that there's let me back up, what they did is they put boreholes between the tanks, and then they sent radioactive survey instruments down those wells, and they measured the radioactivity. And from that, they came up with numbers that they could go from well to well, and they could sort of connect the dots, and they would fill in the areas as solid areas of contamination. So you can see over by SX 9 and 12 that there was a leak, that there was something happening there. and you can see that the leak gets hotter as you go down below the tanks, and probably goes much deeper than what they surveyed. There's also an interesting sort of a little pocket of something going on there right by SX 110 that doesn't seem to connect up with the SX 112 one, and so the question is that a new leak from SX 110 that hasn't been recognized, or is that some of that material from SX 112 that got over there earlier on and now is not connected? So there's these kind of questions, and this kind of visualization really helps you see that. So here's, remember I told you we were going to come back to BY. This is another kind of visualization, the same thing as we did before. You have 2 or 3 different kinds of material happening here. The pinkish stuff is cesium, the blue stuff is cobalt-60, and the greenish stuff that there's not much of is europium. But you can see the cobalt forms a large plume that goes away from the BY 109 tank on the top and somewhere around the C 108 tank at the bottom. What's important, the reason I wanted to put this here, what's important is it doesn't just go vertically down below those tanks like that first diagram I showed you implied. Much of this waste, when it gets into the ground, actually goes off in a lateral. It goes off in a slanting kind of a way. And it's something that hasn't been recognized very well at Hanford, that this movement horizontally is something that is not accounted for very well. Okay. So the next slide is the 300 area. That's the one area we haven't got to yet. This is that lab area that's just north of Richland, Washington. And this is the area where they developed the processes that they use to actually irradiate the fuel and then to dissolve the fuel and go find the plutonium and so forth. So the really important thing here is there are several very large lab buildings. See if I can find my pointer. So here's one right in here that's a large lab building, for example. These 2 large kind of dug out areas right up here are liquid disposal ponds. So they took the same dangerous liquids that they were finding that they have on the Central Plateau, and they dumped them as they developed these processes. They dumped them into these ponds, and these ponds are immediately next to the river. So much of the stuff that you see in the Central Plateau that forms those long plumes has already gone to the river and it's gone. So what's left in the 300 area basically is the uranium. And there are large uranium plumes here that are going down to the south, and they're washing to the river. Every year there's a little bit more that gets in there. And then this round feature right here in the center of the picture, that thing is a test reactor. It's one of like 5 or 6 reactors that they had in the 300 area, and they would use that for all sorts of experiments to develop these processes and to come up with new processes. And they would do things like try to make medicinal isotopes and things like that, just to see if they could. Okay, so there was a legacy of 50 years of nuclear defense production, and that created quite a groundwater problem. This is sort of a sideways view. We call it a cross-section, looking at the whole area in kind of a cartoon form. So we're going to look at reverse wells. Reverse wells were so they would, in here in the plutonium processing plant, they would go through that process. Oh, you bugger. So they would go through this process. I lost my arrow again. They would go through this process of dissolving the rods and coming up with these dangerous liquids that they wanted to get rid of. And one of the ways they would do that was to go over here, and they would just pump it down a reverse well and put it right into the groundwater. And this is very early on, but they did this for quite a while. And so a reverse well is basically not pumping water out, but pumping waste in, and they would put it right into the groundwater, a very bad thing to do. The other way they would get rid of it, of course, as Dirk was telling you, they would put it in single shell tanks to store it forever. Actually, they had a 20-year lifetime, and they've been there since 1940 and 50, so, you know. And of course, those are, you can see the list of baddies that are in those with cobalt and strontium and cesium and technetium, not to mention things like cyanides and nitrates and chromium and all those bad things. So when these tanks leak, and 67 of them have leaked, they go into the groundwater, and they become a real problem, okay? And the other way that they get rid of fluids is they would just dump it into the ground, and they would do that by putting it in a crib or a trench or a French drain. And then the less bad stuff they would go put in the ponds, as I was saying before. And so another really long list of really bad things, and all that stuff gets in the ground, moves through the soils. It leaves long plumes of this stuff all over the place. There are miles and miles and miles of plumes all over Hanford that need to be cleaned up, and it's a really big problem. And the other thing they need to get rid of, is the solid waste. They would, of course, go put it in the burial trenches that you've seen pictures of before. They have landfills that they came along with later, and they even had pits and other things around the large installations that they would throw this stuff into. Now those things are leaching, and they're producing things like uranium and americium, tritium, carbon that's getting into the soil and moving with the groundwater. So this is another sort of a sideways look. You can see those 6 circles up along the river where the reactors were that are leaking things that are getting into the soil and eventually going towards the river. The 2 big areas, the 200 west and the 200 east, where the arrows are in the middle of this site, which are leaking down into the groundwater, and the 300 area, which is right on the river. And all of that stuff gets in the groundwater. And one of the principles you should know about groundwater is that it always goes to the river. The river is usually the lowest spot, and groundwater moves like surface water does. It goes downhill, and it goes down until it finds the river, and that's where it ends up. So the really bad part is all this stuff I'm talking about is going to end up in the Columbia River. So yeah, I know. Here's Dale, and he's a hydrogeologist, and now we got to look at geology, okay? So you have to suffer through a little bit, but I'll try to make it simple. This is what they call a geologic section. And basically what we're looking at is just like if you drilled a hole down through the earth to look at the soils and rocks that are underneath Hanford. To make it really simple, the bottom stuff, that brownish stuff that's in layers, is the basalts. And they're basalt layers just like you see basalts all up and down the Columbia Gorge and other places. And on top of that sits the Ringold Formation, and it comes in 2 parts. The upper part is a sand and gravel and cobble mixture that's cemented together with a clay-y kind of a matrix between those cobbles. And below that, that clay-y part becomes very solid, and you lose all the sand and the gravel part, and it becomes these large, thick zones of clay. And sitting on top of that is the Hanford Formation, which is more like sands and gravels, and fairly coarse. Now, I should tell you that the basement basalt came from, it's called the Columbia River Basalt Group, and it's as much as 6,000 feet thick, and it started happening about 18 million years ago, and lasted for many millions of years, and it's quite thick. It's like 1.5 miles thick accumulation of basalt. The others, the Hanford and the Ringold Formation, came from the Ice Age floods in the northwest of the United States. And what happened was there was this lobe of glacier ice that came down from Canada as those glaciers moved south, and that dammed up the river that came out of glacial Lake Missoula. Right there where that arrow is at the top of Idaho. So I used to live in Missoula, and we used to look at the effects of that. And there's all these wave-cut terraces and so forth, and that lake was as much as 2,000 to 2,500 foot deep before it would release each time. And it did it 100 times. And every time that dam broke, what would happen was the water would get deep enough, and it would start lifting up the ice of the glacier, and the glacier lobe would break, and the whole thing would go screaming across that central part of southeastern Washington. It scraped off all of the topsoil, and that became called, the new name for that was the scablands. And as it came down through the Hanford area, it formed sort of a really big, fast-moving lake, and fast-moving more like a river, and it had so much power it was moving boulders and cobbles and very large sand, and it basically had so much power with all that grit and sand and cobbles that it carved out what is now known as the Columbia Gorge. Okay? So I think I covered everything I wanted to cover there. So it basically formed what you see now as the geography today. And if we look at Hanford, what did it look like at Hanford? At the time, it looked like a big lake, but it wasn't a lake because it was moving. It was moving like a river, and it had icebergs floating in it, and it had a huge amount of dirt and crud, and so it wasn't this pretty blue probably. It was more like a brown. And you have to understand that when one of these things let go, it only took a few days, 3 or 4 days, for the whole thing to fill up and empty. So this was a really rapid thing, and it was like a flash flood. The thing came through in a big wash. It came through and blew past all this countryside, and it formed this very interesting topography. So at Hanford, if we look at Hanford, again, you can see that where the river, let me find my pointer, you can see where the river goes up and around Hanford. So Hanford sits in the middle of this, and here's the Rattlesnake Ridge, that's the south border. Okay, so as the river flowed through here, it created a lot of flow channels where the river ran at different times, and of course it was a lake, so it was running over this whole thing, and it formed first this lower part, which is the Ringold, and then it formed this upper part, which is the Hanford Formation. Okay? So you can kind of get a visualization of how this giant river is flowing through here, and it dumps all this material there, and it's all big, coarse river bar type material. It just did it on a really big scale. So what does Hanford Formation look like? Well, Hanford Formation is medium to coarse grained sands and gravels, and it forms fairly flat horizontal layers. And you can see here this yellow line kind of points out kind of one of these. You can see lots of little layers here, and it's interesting that some of these layers trap and move the moisture, and the vegetation, the grasses, will only sprout up along that layer because that's where the water is. Okay, this particular feature is called the clastic dike, and that's a very interesting feature because it's vertical compared to the horizontal layers of the Hanford, and there's a large question in everybody's mind on how that formed, but it's thought that when that huge volume of water was suddenly released off of the top of these gravels, that there was a upward movement of water in it, and it caused this boiling up kind of a thing on these dikes, kind of a different feature. So what does Hanford look a little, kind of a zoomed up picture here? We're much closer. So now you can see this is a kind of a vertical face that's been carved into the the face of the Hanford Formation, and you can see the layers, the horizontal layers in there, and some of them are fairly fine. You can see there's kind of clayey looking. There's other places that are very coarse. There's not really a lot of sorting going on. It's more like a clump here and a bunch there. Although in some of those layers, you see those little sort of diagonal stripes. Those diagonal stripes mean that that was dunes, and the dunes were moving in the bottom of the river with the current. So that tells you which way the direction of the current was going, and you can see that there was lots and lots of river action happening here, and it wasn't like a lake just dropping things out. Okay, so that's Hanford Formation. So horizontally layered, very heterogeneous, meaning there's coarse things and fine things all over the place. You can tell it had a flow deposit because of the cross bedding. That's those little slanted layers. Some cobble, some sand, and some clays. So let's look at Ringold. And I'm only going to show you one picture for Ringold. Isn't he cute? So Ringold is typically made out of rounded cobbles or gravels, and it's always stuck in this muddy matrix. And you can see that white kind of muddy stuff that sticks all those together, and that's why this cliff stands up here, is because the mud holds it together. And so below this, if you can imagine, just to take all those cobbles away and you leave the white mud behind, you have these thick muddy layers, and they form a aquitard, which basically means they form a layer that will not let the water, the groundwater, flow down through there. Okay, so it kind of protects the layers down below there from what's happening at Hanford. And then below that, of course, are the Columbia River basalts, and we're all kind of familiar with them. We know they happen in big layers. We see them in the Columbia Gorge, but the tops of them aren't solid. There's lots of cracks, and there's lots of things going on in the basalts, and so the basalts really aren't as solid as what you would think. But there's many, many, many layers of basalts around this area. So here's your next groundwater poll question. What would you do? Now you've seen this problem. You've seen the material that it sits in. You've seen the amount of contaminants that are running through the ground. What would you do to solve these contamination problems? And I actually added something here, so I screwed you up, but I'll do this. So would you let the contaminants clean themselves up? Like radioactive decay, after years and years, they would get less and less as they pass through the ground. Would you try to remove as many contaminated sites at the surface as possible so less of it gets into the ground? Or would you pump the contaminated water out so it can't get to the river? What do you think? Well, that was quick. Uh-oh. Uh-oh. There's some movement here. So are we there yet? So we call that good. So it looks like about 60% would remove as many contaminated surface sites as possible, and 40% would pump the contaminated water out. And I kind of cheated. I added one more option that says, oh, do some combination of all of these. And that's really the best answer, because none of those three is really going to get all of it. And none of those three is going to be, even the combination of those three is not going to be the entire answer. So the answer is, excuse me, the answer is you try to remove as much of the contaminated surface as you can possibly get at. You try to pump out as much of the contaminated water that you can so it won't get into the river, and you treat that water. And then what you can't get, you try to make it possible that those contaminants will decay before they get to the river. So we try to use all three of those things. Those of you that answered remove the contaminants and pump the contaminated water, those are probably the better answers, in my opinion. I'd rather not let it just sit down there. But it's a combination of the three, and thank you for doing that, and I didn't mean to fool you. So the groundwater problem. How do you undo 450 billion gallons of radioactive and chemically dangerous releases, both planned and unplanned, to the ground? It's just a huge problem. You can imagine 450 billion gallons, okay? Well, first, as I said, you try to get the worst parts of the problem solved, and then you try to get as much of that as you can. So you go after the absolutely worst parts and work on them first, which they basically did. And now they're trying to get as much as they can. The problem is always complicated by the fact that they had hundreds of different sources, I should say hundreds of sources, and scores of different kinds of contaminants that are all associated with varying dangers. So there are different kinds of radioactive elements, different kinds of radiation, beta, alpha, gamma kind of radiation, and they all have different half-lives. Some of these are very long-lived that last, 30,000 years for a half-life, 300,000 years before they're safe. And they're mixed with chemical compounds that they use to dissolve them when they pour them in the ground, and so they have all sorts of chemical problems as well. And mixing these things together is just a bizarre kind of a thing. Okay. So what are some groundwater remediation techniques? Well, what do we do? What kind of techniques can we use to get at some of this stuff? Well, obviously, the first one we talked about before was source removal. We would try to get out some of those surface sites and get that stuff out of the ground so it doesn't leach into the groundwater. But the problem is it's hard to get at all of it by digging, because obviously these plumes are huge, and you start out at the worst part of it and you start working your way out until you get to a point that you say, well, it's not so bad now, maybe we should quit. And then once you dig all this soil up, where are you going to put it where it's going to be safe? You have to put it somewhere where it's not going to, again, leach into the ground. So, and it's almost impossible to try to treat it as soil. It's a very hard thing to do. You can use vapor extraction if there are gas-type organic chemicals in the soil. You can pump the soil air out of the ground and remove those. That kind of works, especially for carbon-tetrachloride and things like that. There are pump and treat systems which use resins that have ion exchange properties. And what that means is when a dangerous ion comes along, like strontium or something like that, the strontium will exchange with this medium, and strontium likes to exchange with calcium, for example, and the calcium will go away and the strontium will stick to the resin, and after the resin fills up with strontium, you take it out and put some more in. And so this is a good way to try to do things like uranium and strontium and chromium. And this is the basic approach that the Hanford folks, the DOE folks, are taking at Hanford, and especially for chromium. Right now they've built a brand new plant, I'll show you in a minute, that uses a multi-element pump and treat on the central plateau, which also has a bioreactor. And the bioreactor is a thing that uses bacteria, and it removes nitrogen and carbon tetrachloride, and I'll talk about that in a minute too. And then you can use what are called permeable reactive barriers. And so basically what you do is you inject stuff into the ground in wells, and you form this long linear injection zone that's full of this stuff, and then that stuff captures the element you're trying to get rid of. And the big one is strontium. At 100 N, they were using apatite to catch strontium, and that seemed to work pretty well. At 100 D, they were using a different kind of a thing where they were changing the reducing environment of the soil, and they were converting hexavalent chromium to chromium that isn't dangerous. And as soon as you convert it, instead of being mobile in the water, it suddenly wants to mineralize and come out. So it was a very effective way to do it, and I'll show you that in a minute too. And then in the 300 area, they were trying to do fixation, and the idea was to use phosphate, and they were going to either let it soak in the surface or inject it in wells, and it was supposed to attach itself to the uranium and form a uranium mineral, similar to what the strontium was doing. And then the last thing I should talk about is phytoremediation, and the idea was that they would plant certain kinds of plants that would uptake water, and they would, for example, they were using at 100 N coyote willows, and they would uptake groundwater, and they would extract the groundwater. The strontium would get stuck in the new growth of the willows. At the end of the year, they would go out and they would trim off all the new growth branches and so forth. And then next year, the willows would grow again and take out some more. So it worked fairly well. The problem is the roots don't go very deep, so it's not very effective for deep things, and it does not work very effectively. So it only sort of finishes the problem. So this is just a cartoon to sort of give you a visual on how some of these things are working. The thing on the far left is a reverse well, and that's just groundwater, so that would be caught by the pump and treat. I lost my little guy again. This is a plant dumping stuff in the ground. This is a tank leaking. This is a crib or a trench that's leaking stuff into the ground, and these are solid waste in a trench that's been buried. And so you have a groundwater pump and treat that's pulling water out of the ground, and it's treating it, and then it would have another well that would send the water back down again. Vapor extraction, they would pump out air, soil air, and they would take out the vapors. Down here, they're removing some of the sources, trying to get that stuff out of there. They have another groundwater pump and treat down here on the river. And then right next to the river, they're trying to catch what gets past the pump and treat. They put in a fixation site. And then this whole thing, they're talking about natural attenuation, that some of these elements will decay before they get through this process down to the river. And they were used to count on this thing being decades, if not hundreds of years long, to go from where the plume hit the groundwater to the river, but now we know it's not nearly that long. So first of all, source removal. So obviously you demolish and remove the buildings that are contaminated. You dig up contaminated soil. In the upper left hand, you can see where they're digging up burial grounds, taking out the barrels. The picture at the lower left is a trench that's been dug up. The right-hand picture is that Z trench, one of the Z trenches I think this might be the one you were looking at before, and you can see that they've removed a heck of a lot of soil trying to get at some of the contaminated soil on the bottom of that trench where they let the water soak in and go to the river. So one of the ways you can treat this is to try to remove as much of the source as possible at the top. In the early days, they started some pump and treats. They had, you can see here, several pump and treats along the river. Let me see here. I think there were 1, 2, 4 pump and treats, I think, along the river there that were pumping in those different areas. Most of them were after the chrome. They actually started one at 100N that was a strontium pump and treat that did not work. They had a hell of a time with that one. And then up on the central plateau in the 200 West area, they were very worried about that carbon-tetrachloride problem. And they had both a vapor extraction system there that worked pretty well, and they also had a pump and treat that only kind of worked. And then they had one small pump and treat down to the lower right that was getting out a very bad spot of technetium-99 and uranium. And that pump and treat, I think, has just been converted to something else. So these are the old pump and treats. Currently, this is just the river. I'm sorry for this being such a busy slide. I know it's a lot to look at, but I'll try to help you go through this pretty carefully. The blue areas along the river there are plumes of chromium. And the lower left-hand one is the 100K area. You can see it's already been cleaned up to a fairly large extent. They have a pretty good pump and treat going there. The graph to the upper left is the K graph that shows you from 1997 to 2011 that's the cumulative amount of hexavalent chromium that they've taken out of there, which is the dangerous kind. And it's gone from just a little bit in 1997 to way better than 600 kilograms of chromium by 2011. The upper two blobs of blue, the two plumes of chromium, are actually connected. That goes across that point up there, and that's called the horn. The one on the left is the D area. The one on the right is the H area, even though they're both called HR. All those little triangles are wells. Some of them are extraction wells where they pull the water out. Some of them are injection wells where they're putting the water back in. And the idea is to put the injection well near the river so it kind of builds a water mound and pushes the contamination back towards the extraction parts. Okay, and that graph to the right, upper right, is the H and D areas, and their cumulative removal of chrome, hexavalent chrome. And you can see that by 2011, they started up the new DX system on top of everything else. And at the very top of that, you can't quite see it, but the HX just started up there as well. And they're well above 1.2 metric tons of hexavalent chromium now that they've extracted from that area. Okay. Now, just as I'm just going to point this out briefly, that little yellow plume that you see there in the N, 100N area, is a strontium plume. They tried to pump and treat that thing, and it didn't work. It did not work at all. All it really did was it kept that plume out of the river because they, again, formed that kind of a wall of water. So what they did, this long black line, they created the permeable reactive barrier I was talking about. And so what they did is they drilled a bunch of very close spaced holes. They injected calcium citrate and polyphosphate, you don't need to know these things, into those wells, and those solutions combined and formed apatite under the ground in areas that were probably 100 feet in diameter. And all these wells overlapped with each other. So they formed this fairly solid curtain of apatite from one end to the other. And the interesting thing is when the strontium tries to move through that permeable barrier, the strontium is attracted to the apatite, the calcium is released, the strontium is grabbed, and it's just like an ion exchange resin, and it grabs that strontium and keeps it out of solution. It has worked very well. It's one of the things at Hanford that's worked as well as they predicted. So here's a sideways look at that. You can see off to the right over here, the strontium plume is coming out of 100N, getting into the groundwater and moving towards the river. Here's the injection wells that they put in, and they built this apatite barrier under the ground in the sands and gravels. And as the strontium moves through that barrier, the strontium gets pulled out, and clean water goes through the barrier and ends up in the Columbia River. So it works very, very well, and it's one of those success stories at Hanford. So if we move up to that horn again, the area to the left is the D area, the 100D. The area to the right is the 100H. While they actually had a reactor over at H, a lot of this pollution, this contamination, actually started at D and traveled across the horn. And so that chrome plume in the in the top and right-hand sides actually has been traveling towards the right. The exception to that is and I should say they have a number of pump and treats working in this area right now in both the D and the H area that are working very hard on getting this stuff, and they just started this stuff up like last year. The new pump and treats just started up last year. The one area that did not work is to your lower left, and that part of the plume that's down to the lower left was getting into the river and was causing a lot of concern. So they had to do something different. So in this area, they actually came up with this horrible name that nobody should try to remember. It's the In-Situ Redox Manipulation Barrier. And what that basically is you can see the faint line of gray little circles going across from left to right across that top of that plume right there. And those circles, they injected nanovalent iron in there. But basically all that did was it created a reduction zone. Rather than being oxidized, it was reduced. So there's a reduced zone that goes across there. As the chromium got close to that, it would convert to chrome 3 because it was reduced, and it would fall out and become mineralized and become part of the formation. The one place it didn't work, you can see that there's a spot where it kind of broke through and headed for the river. That was a problem, so they brought in a very small pump and treat system that sits right there and works on that. Okay? And it looks just like that. There's a little pump and treat facility pumping away, trying to get that chrome and keeping it out of the river. And you can see how close the river is. It's not that far away. Okay? And that's what a typical pump and treat facility looks like along the river. They're very small. They're not very big. And if you look at, see if I can get my pointer to work. If you look at this little line that kind of runs around here, that's some of the piping going off to the different wells coming into this. So this is probably the pump house, and in here are the resin columns, and I'll show you what a resin column looks like in a minute. So that's a pump and treat facility on the river. Okay, so how well do these things work? This is a graph demonstrating over the years from 1997 again to 2011. Starting from the left, this red line starts up about, if you use this scale on the right-hand side, starts out above 100 milligrams per liter, and through the years down to 2011, the water coming into this facility has dropped down to considerably less than that, probably only about 15 or 20 milligrams per liter. So it's working very well. The water's cleaning up over time. The problem is, of course, if you look at this blue line, the blue line is removal efficiency. How well is this system working? And as time goes on, its efficiency is going down as well. So eventually what's going to happen is the efficiency is going to drop below what you can get out, and it's not going to work anymore. But hopefully we're going to be down to a point in terms of how many milligrams per liter there are left in the water that we can shut the system off and let it be good. Okay? So remediation should be complete at that point. All right, so now we need to look at the Central Plateau, and it's a mess. If you look at this Plume map, this is the whole Central Plateau. The 200 west is on the left, the 200 east is on the right. You can see 200 west and east actually have different chemistries. They have different plumes, different kinds of materials. The light green stuff You see there is carbon tetrachloride, again, that's that plume. The sort of dark red stuff is uranium. Technetium-99 is in the yellow. The bluish stuff is nitrate, dark blue is nitrate. The light blue is tritium. And there's some brownish stuff that's the chromium, and they keep changing colors on me, so I'm sorry, I'm using their maps. So 200 West is a very complex overlapping problem, but it's not moving very far, and it's easier to capture. That's where they set up the new pump and treat system that I'll show you in a minute. 200 East, you can see that there are very large plumes that are going north, west, and southeast, so going up and to the left and down to the right. The ones that are going down to the right we talked about before, that's that big tritium plume and the big iodine plume that are heading for the river. That's the blue and the kind of orangish color. You can see, though, north of 200 East, there's some big plumes of technetium-99 that they really got to do something about. The little purplish guys are strontium. That's also a baddie. The red ones are uranium, and they definitely got to do something about that. And so this is a large area that really needs a lot of work. So let's zoom in a little bit on 200 West. That's the one they're working on. This is the plume map that they made when they built the new facility, so they could see what they were working with. You can see that these plumes overlap each other. There isn't just one element in any place, there's a bunch of them. So they had to come up with a process, a facility that could handle more than one thing at a time. They had to come up with this very large building. If we look at it sideways, it's even complicated more by the fact that, remember that aquitard mud that's at the bottom of the Ringold that keeps things out of the basalts? That's that brown layer you see going across the bottom of here. This brown stuff that travels here and here. But you can see it's been removed by the river when it used to flow through here in the middle. And so this stuff is going right down, and they're pretending that it's not getting into the basalt, which is that black line. Okay? But you can see that this plume actually gets underneath that clay layer, that mud layer, and it's getting into the basalts. And so it's a much bigger plume, much bigger problem than they're recognizing. And so there's probably pathways here that we haven't even started to deal with yet. So how do we deal with that? Well, here's the 200 West pump and treat facility. It's just under construction. This is what a ion exchange rosin bed looks like. I told you I'd show you what they look like. They look the same in the river corridor. The outside, these are the bioreactors. Those are those tall columns there that digest carbon tetrachloride, nitrate, and to a small extent they fix the chromium. The exchange beds are inside. The valves and the important stuff are on the inside that can get damaged. The outside is the stuff that can sit in the weather and won't harm it, but it's big. So how well does it work? So the remediation techniques, some of these, like these giant pump and treats and the bacterial degradation, have never been used on a project this large in either area or in volume of water. Some of these techniques, like this fixation of uranium I was talking about using phosphate, have never been tried before. It's something brand new, and they're going to try it here as a first time. And most of the decisions they're making here are all made on models. They run a model and they say, see, it works. Well, yeah, maybe. I don't know if I trust models that have to go 500 to 10,000 years into the future. And models really aren't made to be reliable that far out. Future problems, there are uranium plumes. This is a uranium plume that was predicted by a Hanford model to appear in 2035. And I think Ken Niles showed this in his program. This material is now hanging in that dry zone above the water table, and it's going to slowly drip down and get into the water table, and in 2035 and later it's going to be a problem. So this is something we have to deal with in the future. And there are problems that haven't yet been addressed, like the burial grounds. Do we cap these burial grounds? Do we dig them up? If we dig them up, it's, where do we put the stuff we get out of there? It's a very big deal. And we were talking about the tank leaks and the stuff underneath the tanks. One of the proposals has always been that they want to empty the tanks out of all the stuff that's in them and then fill them up with concrete and put a cap over the top and never dig under them. Well, as a groundwater person, I find that just abhorrent, because this is where some of the worst stuff is that's leaked out of those tanks. So this has to be addressed, and it has to be something that's going to happen in the future. So what can you do to help? This is your part, okay? Obviously, those of us that have been doing this a while aren't going to be here forever. So you need to become an environmental advocate. You need to add your voice. You need to go find one of these environmental activist kind of organizations, the Hanford Watch or Columbia Riverkeeper, somebody like that, and join. You need to educate yourself about what's going on around you, especially about Hanford cleanup. My education was as a geologist and a hydrologist, but Dirk was a nuclear engineer. Paul, that you're going to meet next time, was a ecologist. There's all different kinds of people that get involved in this, and we need everybody. So, and of course, you need to pay more attention to what's going on around you, because a lot of people I've talked to have never even heard of Hanford, and it's a real problem. Okay, so you need to jump in here and help us. We need some new bodies. So here's your last poll question. So what's more important to making the groundwater cleanup decision? Is it going to be the cost to the taxpayer? Is it going to be the risk to the public as drinking water? Or is it going to be removing the contaminants to protect the environment? So are we there? Okay, so let me say that, again, I wasn't being very fair. Okay? I agree with you. My being a hydrogeologist, my whole focus is getting the contaminants out of there for protection of the environment, because you don't want all that stuff in the river. Protecting the public as a drinking water thing will be, excuse me, hundreds of years in the future. I think if they paid to put that stuff in the ground, they're going to have to pay to get it back out. And as taxpayers, we need to face the fact that this is something we need to spend money on. And, I understand that we're paying $2 billion a year to get rid of this stuff, but it's one of those things we need to deal with. Okay, thank you very much. Now Becky's going to talk to you about public involvement.
Thanks very much, Dale. It was very interesting. Hello, everyone. I'm Becky. I'm the Public Involvement Coordinator, and we're going to do things a little bit different this week because we've had so many problems with video. So from now on, I'm just going to do presentations after everybody's finished with their more technical presentations. So since the first week and the second week, video did not really work, and you couldn't really hear. I just want to catch you up, and then we'll talk about this week's topic, which is how to make public comments. So the first week was really just focused on what it means to participate or get involved at Hanford. It's a very big, very complicated place, and at first it seems difficult to imagine how individual citizens can contribute. Really, simple conversations with your friends and community members are a form of involvement, and we'll spend a few more weeks talking about other forms of involvement. But first we're going to focus on the most common form of contribution, and that's trying to influence the decision-making process through public commenting. Public participation is required for many decisions that are made at Hanford, specifically the ones that fall under one of the following laws. And some of you might be familiar with these, and some of you might not be, so we'll talk about them briefly. So those laws are CERCLA, or the Comprehensive Environmental Response Compensation Liability Act, RCRA, which is the Resource Conservation Recovery Act, and NEPA, which is the National Environmental Policy Act. These laws can be considered environmental laws that relate to different types of cleanup and related matters at Hanford. CERCLA oversees the cleanup of Superfund sites, and Hanford is a Superfund site. RCRA is a hazardous waste cleanup law, and NEPA mandates that actions taken by federal agencies or on federal land need to be assessed for their environmental impact. They all require assessment documentation of some kind or another, and the first step for that is usually called scoping, and all of these have different terms, so these are sort of general terms. But the first step is called scoping, where an agency goes into the community to try to identify concerns in order to understand what topics and to what degree they need to be addressed in the next step of the decision-making process. And that step is called publication of a draft environmental assessment or environmental impact statement. Once the draft is released, the public can review it and provide further comments. And then agencies use this information in the final draft, which usually issues the decision, which isn't always true, but we'll say it is for now. So make sure to go back and look at the week 1 public involvement packet to learn more about the laws, more about what they say about public involvement, and that there are other resources in there that talk about other organizations, things of that nature. Last week focused on how to actually access resources that help you locate and understand upcoming proposals. Calendars are the easiest resource for basic information, and each agency has one. You can see some of the images on here. Of course, there are links to all of this in the packet. In addition, the tri-party agencies have a public involvement calendar that you can download from hanford.gov, and that image is right here, and you can see the link, and it will download a PDF to your computer. But make sure you look at the packet to learn more about the tools within the calendars that make it easier for you to locate information, because they're all a little bit different. In addition, there are in-person opportunities for learning and getting information. Some organizations sponsor social events such as ice cream socials, kayaking trips through the Hanford Reach, and they create more casual opportunities for Hanford discussions. And the neat thing about these is that not only are you learning about Hanford, you might also meet other people who share your interests, and you can start building a Hanford network, which is really useful. Other organizations offer pre-hearing meetings and workshops that you can go to get help with developing your comments, or if you have questions about a proposal, there are sometimes groups that will be at meetings to help you. It's important now that you start to consider yourself as a resource too. You're devoting time to this, you're going through the leadership initiative, draw on what you've learned and organize an event. A great way to do this is to use a program called Inheriting Hanford. This program has Hanford mentors throughout Oregon and Washington who know a lot about the site and are ready and willing to share their knowledge with you and your community. In fact, Ken from the first week and Dale are both mentors. So if you have some free time, go check out the website, and you can get an idea of who's around you and who you can contact when you have questions or if you want help making an event or something along those lines. So for this week, you understand the laws. You know how to access resources. Now it's time to actually make your comment. And you can do this a few ways. You can do it online, by mail, or in person. And each method has its benefits and drawbacks. The most significant drawbacks are mailing letters takes more time to arrive, and I know personally I'm really bad about actually remembering to put things in the mail. And some people feel nervous making presentations in front of others. So there are benefits to each one too, though. So in-person commenting allows you to attend pre-meeting hearings and to learn from others in your community. And online is quick and easy to do, and a lot of us are accustomed to communicating that way. The downside of some of those is also that you are usually limited at a meeting to just a few minutes. So if you have really long comments or comments that you think will take more than 2 or 3 minutes to say, make sure to submit your comments online or by the mail. So now you have an idea of the venues through which you can submit your comments. Let's talk about what they're actually going to say. You've done your research, you've talked to somebody to get clarification. So what do you actually write? So I'm going to talk about a few things, and these are really guidelines for content, but you can consider them also a template. So if you just don't know where to start with writing them, you can sort of follow this. So public comments should be respectful and easy to follow. They should identify the precise section or area of concern from the document. They should state your concerns about the issue, and when you're stating your concerns, you should complement those by resources or citations for facts that you use. So make sure if you claim something, provide a link to a resource so that the people who are reviewing your comments can read more about what you're talking about. And then this might be the most important one. Propose a potential alternative solution to the problem. It's really basic, but it helps the people reviewing comments. So that's really all there is to it. The packet I sent out provides a lot of information, a quote from the Council on Environmental Quality's Citizens Guide to NEPA, which is a very useful tool and will help you better understand the commenting process, not just at Hanford, but in general. And if you want some examples of comment formats, you can also look at the links that I sent in the last part of the packet. You'll see that not everyone follows the same format I gave you, but that's okay. The format suggested is based on what agencies find most useful for public comments, but you're free to format them how you like. So make sure to review those links and get a better meeting or get a better idea of how meetings and commenting goes. So that's all I have for tonight. Feel free now to send in your questions for me and for Dale, and we'll get them answered. Okay.
And this is Dale again, and thank you for attending. This has been an interesting webinar series already, and I've enjoyed being here tonight.
We're just waiting to see if there are any questions. If you have questions, let us know here. We'll give you a few minutes if you need to think about how to write your question. So here's the first one.
So the question is, does a model exist to predict the potential Columbia River contamination, and would this amount of contamination constitute an acceptable risk to the public? So that's a pretty good question, and the models basically are made to predict what's going to come in the groundwater and how the contamination moves in the groundwater. And at this point, there has never been a connection between what's going on in the groundwater plumes and what ends up in the river. There has been an assumption, and the problem with Hanford has always been that it's a process of assumptions. There always has been an assumption that the Columbia River runs fast enough and has a big enough flow that whatever gets into the river will be diluted by the time it gets into that water and moves downstream. So the answer is no. There's not really a groundwater model that hooks up to the river. They should do that. They have not done that, and it's because they don't want to recognize the fact that some of the contamination gets there. The next question is, how has contamination affected native aquatic fauna? That's a really good question, and again, this is one of those places that the Hanford scientists have never really wanted to look, and I shouldn't quite say that because there have been studies in the past, but this is something that doesn't get reported very much. Just recently, Paul is the Oregon member of the Natural Resource Trustee Council. He will be here next week. The Natural Resource Trustee Council has started a study that's looking at upwellings, which are basically the groundwater coming out of the river bottom and affecting the critters in the bottom of the river. And they have looked at some of the past data that's been collected, and it's obvious, and I had no idea, there are mussels that live in the bottom of the Columbia River that are freshwater mussels. And there are vast areas, particularly close to the reactor areas, that there are no mussels. They're gone. And the problem is that, you know, the Hanford Reach, that part of the river that's next to Hanford, has never allowed a dam to be built. And so it's one of the few parts of the Columbia River that actually are free running and have riffles. Excuse me. And salmon and steelhead in particular have to have riffles to make their redds, their egg-laying beds in. And so it's one of the few places in the Columbia River that the salmon really love to come to, and that's exactly the place where this water bubbles up in the bottom of the river. So there's never been a study to say how badly the pollution that comes out of Hanford affects the redds. And it's one of those studies that's coming up by way of the Natural Resource Trustees. So we're just at that point in time when things are starting to happen where there are folks that are actually looking at the river and looking at the critters in the river and also on the land for that matter, and how they have been affected and what's it going to take to restore that resource to get those the bottom of the river cleaned up and get those fish and invertebrates and clams and so forth all back in there again. So that was a really good question. Thank you.
All right. Well, if you have any other questions, go ahead and send them in. We'll give you a minute. And Dale, do you have any?
I have a couple of comments to make since we don't have a question sitting here yet. There's two things I want to sort of mention here, and as folks that might be coming forward to work on Hanford, that might be something you could think about doing with your time. One of the things that occurred to me is that, we've looked at Hanford as a decades-long process that's gotten to the point where we came along and started interacting with it. And it's been a process of assumptions. They always assume that this is happening or that's happening. That for an example, they assumed that the groundwater took 100 years to get to the river, or even thousands of years to get to the river, and it turned out it only took 5 or 10 years to move that far. And so these assumptions are proving to be, I won't say invalid, but not very correct. That they need a lot of fine-tuning. So one of the things we can learn from Hanford is not to base our decisions on assumptions and to use a different method. And I'm not really sure what that means, but I think it's something that we could work on. And the other thing is, what we're doing now, let me do that differently. The guys who were working at Hanford at the time in the 40s and the 50s and the 60s were doing what they thought was fairly environmentally responsible. They were putting stuff into the ground, and in those days, you had a dump, you dug a hole, you put all your trash in there, and you buried it, and it was fine. And they thought, scientists told them, they thought they could put these liquids in the ground, and the ground would absorb them. That all that bad stuff, all those radioactive elements, and all those chemicals would get absorbed by the ground, and it would hold it. And of course, they didn't pay much attention to the fact that we're turning out billions of gallons of material, and they were trying to get the ground to take that. And of course, as a current day hydrologist, I can tell you that things don't stay in the ground in one place; they move. So, what are we doing right now that we think is fairly safe? I'll give you a good example, and that's Erdf. We have this giant landfill. We're putting all this radioactive and chemical waste in terms of contaminated soils and building materials and all this kind of stuff. And then we're going to put a lid on it, put a cap over it, and say it's good. Well, is that really? Or is that something that we're going to have to, somebody generations from now is going to have to come back and dig it back up again because it was a stupid thing to do? But at the moment, it seemed like a pretty good idea. So one of the things we need to consider is in 20, 30, 40 years from now, what are we doing now that's going to be a bad idea in the future? And that would be something that would be real fun to look at. Okay, the next question is, of all the contamination, which is the worst, most important, or most urgent? That's a really tough question. One of the reasons they're trying so hard to get the carbon-tetrachloride out of the 200 West area is they feel that that's a really bad contaminant, and it has a lot of implications in terms of risk to human health. And so typically what they do at Hanford is they go through this long process, environmental sort of a process, to figure out how much risk each one of these plumes holds and how much damage it would do if it were allowed to contact creatures or humans. And so we go through this long process of risk development to decide which of these contaminants we should clean up first. And they actually, for example, along the river corridor, they go through a long process that's called the remediation. The remediation, investigation, and the feasibility study to determine exactly which of the contaminants are the ones they need to deal with and which ones they don't have to deal with. And the ones that have enough risk, they will go in and try to clean up. And the ones that have just a little bit of risk but maybe acceptable, they decide to leave there. So they go through this process of risk development, and they decide which contaminants are the worst. So your question is, it depends on where you are. In different places, there are different contaminants. Along the river, probably the more important contaminant is the chromium because it's dangerous to the critters. And it's very bad on fish. It's of course, very bad on things like mussels and invertebrates and things like that. But there are other things, strontium, the strontium plumes, the cesium plumes, and so forth, would be very bad if they got into the river as well. In my opinion, the iodine, I've talked to several people who thought the iodine 129 is a very bad element. They don't seem to be treating it very importantly, especially the big plume that's heading to the southeast, down to the river. And I don't think they intend to try to treat that. And that seems to be a really bad thing to me because iodine has always been a serious cancer producer. All right, what have you found most interesting working on Hanford issues? What's the most interesting? I guess probably the most interesting thing has nothing to do with science, and it's the fact that these problems get worked out almost by committee. There's so many people with their fingers in the pie that it's this huge excuse me, undertaking that so many people try to get together and collaborate to get these problems to be fixed. And just as a small example of that is that there's the Hanford is considered a Department of Energy problem, and they become the responsible party. And then the United States Environmental Protection Agency, EPA, and the state of Washington Department of Ecology get together, and they are the regulators. So those three organizations, EPA, Ecology, and DOE, are called the tri-party agencies, and they make huge decisions about all the stuff they're going to do. They throw around $2.3 billion a year on their cleanup costs and so forth. And so the interesting part is the policy, is the giant waves of decisions that are going around. Okay, so the next question is, I'm sorry, but this is a real basic question. Does groundwater run through all the layers of rock and soil you mentioned, like the Columbia River basalts and the Ringold Formation in Hanford? And the answer is yes. One of the things that they've discovered most recently is that even the muds, even those things that are considered aquitars that aren't supposed to have Hanford water running through them, actually have contaminants in them, which means that the water does get in there. And the problem is that once the contaminant gets in that mud, it stays in there. So even if you clean out the gravels up above, that contaminant comes back out of the mud and it keeps polluting everything. It recontaminates the water. So yes, and as I said, they are just now looking at the place where the river removed some of that lower mud from the Ringold, and now they're finding places where the contamination has gotten down into the Columbia River basalt and is moving in the basalts. The problem is nobody knows where it goes once it gets in the basalts and then goes underneath the Ringold and the Hanford, because we don't know where it comes out again. So the really tough question is, where does it go and what are we going to do about it? And is it even possible to try to get it back again? And who's it going to affect downstream? Good question, though. I like that one. So we probably have time for one more question. So let me make one more plea for you guys. This is a place where if you want to be a scientist, or if you want to be a policymaker, or if you want to be a manager, this is a really good place for you to try to get hooked up. This is a place where you can put a lot of energy. Dirk has done this, and Ken have done this for like 20 years each. Dirk the other day was adding up how many years each of us had added. If we added it up all together, how much time we had, and it was in the 70 or 80 year category between the four of us. So we're getting kind of long in the tooth now. We're looking for folks to join us. I can imagine that if you were in college right now and you wanted to do something like this, that I could certainly see you taking my place or Dirk's, and we'd be happy to let you help. I want to repeat what Becky was saying, that I am one of the people at Hanford that started this idea of mentoring younger folks to become people who would be involved at Hanford. It's not that onerous a kind of a thing. If you want to become a mentor, we will take you along to one of the HAB meetings. We will let you see some of the documents we're dealing with. We can kind of show you what the process looks like. You don't really have to do anything right off. I mean, we're just kind of showing you what it's all about. The idea is to sort of give you an idea of what it is we do, and maybe you would like to be part of this process as well. And as it turns out, there's a few people that are starting to show up at Hanford. Becky is one of the new ones. There's some other folks up in Washington that we've met that are fairly newcomers, and it's nice to see new faces. So how about you?